So your quiz will be similar in format to this quiz, same format, and it will be limited to deadlocks. So the material is limited, but you will have to understand the material thoroughly, and you have to be precise. When you read the questions and when you answer the questions. So you have to read the questions carefully. Okay. So the first question is true or false. In theory, no deadlock can happen if all the resources in the system are preemptive. True or false?
True.
Yeah, this is true because a necessary condition for deadlocks is no preemption. No matter how many processes are involved in a deadlock, it may be possible to recover from the deadlock by terminating only one process.
True.
Yeah, this is true because it's saying it may be possible. It's not saying that it's always possible. And an example is you can have any number of processes in a circular weight. So you can have P1, P2, all the way to P1000. And then if you have this circular dependence, you have 1,000 processes, but if you terminate any one of them, you will no longer have a cycle and you will no longer have a deadlock. So one process resolves the deadlock. If the banker's algorithm for deadlock detection indicates that the system is in an unsafe state, that does not necessarily mean that there is a deadlock in the system.
True.
So this is false. False because we are talking about the detection version. So the detection version, if the detection version does not find a safe state, then there is a deadlock because the detection version does the analysis after the fact, while the avoidance version tries to avoid the deadlock. So if we change this to avoidance, if the avoidance version of the banker's algorithm indicates that the system is in an unsafe state, that does not necessarily mean that there is a deadlock, this would be true. So for the avoidance version, this is true, but for the detection version, this is not true. So that's why you have to read the questions carefully. A process that is holding resources, but is not waiting for any resources, may cause a deadlock if the number of resources that it's holding is sufficiently large.
False.
False, because a necessary condition for deadlocks is hold and wait. So you'll have a deadlock if you have processes holding and waiting, and if you have a process holding 1 million resources but it's not waiting for anything, then it's not going to cause a deadlock. Circle the right answer. Which of the following will not prevent deadlocks? Now, 3 of them are actual deadlock prevention methods that we studied in class. So let's recognize them. Don't allow a process to wait for resources if it has resources allocated to it. Yes, this is a method that we studied in class. By the way, they're all theoretical, but this is a conceptual question. Impose a total ordering of all resource types and require each process to request resources in that order. Again, this is another prevention method that we studied. Require each process to request all the resources that it needs before it starts executing. We have studied this as a prevention method. D, set a limit on the number of processes in the system. So this is something that we did not study. And obviously, setting a limit is not going to prevent deadlocks because it's not about the number of processes. It's about the relation between processes. And you can have a deadlock with only 2 processes. Okay. A system has one resource type with 10 instances. Given the following state, which of the following is a safe sequence? Okay. So first question is this prevention or detection? Is this question prevention or detection?
Prevention.
Okay, I heard both answers. Okay, so who can justify their answer?
This-
Yeah, someone with a justification. Yes?
It's prevention because you're trying to find a safe sequence. It's not like you're trying to find a problem already.
Well, but even with detection, we look for a safe sequence, right? Even when in the detection, we still have the notion of a safe sequence. That's not what makes it prevention.
It's detection because processes have current allocations.
No, you always have current allocations in both detection and prevention. There is always a current allocation. But what you have with detection and you don't have with prevention is the current requests. So in prevention, you have the maximum needs, right? And you calculate the future or the projected need. So well, in fact, the next question is detection. So, okay, why is this scrolling? Okay. So this is prevention because each process is declaring its maximum need. And we know the current allocation. So based on maximum need and current allocation, we calculate the future need. So prevention is about analyzing the future based on expected or projected needs. Detection is about analyzing the present only. So with detection, we have the current allocation and we have the current request. So the requests that we are analyzing in detection are actual requests that processes are making now in the present. While the requests that we are analyzing with prevention are expected requests, are future requests that we expect processes to make based on their declared maximum needs. Okay? So now, given that this is prevention, we calculate the expected need for process 0, process 1, process 2. So it's just, we subtract. So process 0 declared that it will need a maximum of 6, but it currently has 1, so it will request 5 more. Process 1 will request 7 more. And process 2 will request 2 more. And what do we have available now in the system? What we have available is, this is what is allocated, 6. So 6 subtracted from 10 gives us 4. And we look for a safe sequence with 4. Which needs can we satisfy? P2. So we can satisfy P2's needs. Then P2 is going to release this, 3, so we'll have 7. Now with 7, we can satisfy this and this. So how many safe sequences do we have?
2.
So we can do either P2, P0, P1, or P2, P1, P0. Okay, so there are 2 safe sequences, P2, P1, P0, and P2, P0, P1. So the answer is both A and C are correct. Now this is the detection. A system has one resource with 15 instances. Which processes are involved in a deadlock? So let's analyze this. Now we have 3. We have 4 processes. So this is detection, so we analyze based on the current requests. So we just need to calculate available, and available in this case is, this is current allocation, so 4 plus 1, 5 plus 5, 10, 12, subtracted from 15 is 3. So available is 3. Now, available is 3, so which process can go first? We can satisfy the needs of P3. So we put P3, then P3 releases the current allocation, which is 2. So it releases 2, we will have 5. Now 5 can satisfy the request of P1, so we put P1, then P1 releases one more, so we'll have 6. Now we have 6 and we have the remaining processes requesting 7 and 8, so we can't satisfy any of these requests, so we fail to find the safe sequence. And processes P2, P0 and P2 must be in a deadlock, because what they are currently requesting cannot be satisfied by what's available plus what will get released by these. What they are requesting is held by, what each one of them is requesting is held by the other, P0 and P2. So P0 and P2 are waiting for each other, and P0 and P2 are involved in a deadlock. Okay, and now, questions on a system with processes 1 through 5. P1 is waiting for P2. So you have to draw it here. P1 is waiting for P2. P2 is waiting for P3. P3 is waiting for both P4 and P5. P4 is waiting for P5. And P5 is waiting for P2. Okay. Answer the following questions. Which processes are involved in a deadlock? So the processes that are involved in a deadlock are the processes that are in a cycle. And we have this cycle in red. So this is one cycle. And we have another cycle which is, we start from P2 and we go this way. So this is an alternative cycle. So we have two cycles that involve processes 2, 3, 4, and 5. So these are the processes that are involved in a deadlock. Any questions? Okay.
So P1 is not involved in a deadlock?
Yeah, no, it's not. So by our definition, a process is involved in a deadlock if it's on a cycle. So if it's one of the processes that is causing a deadlock. So it's waiting for P2, but by our definition of involvement, it's not involved in a deadlock. So our definition of involvement is the processes that are waiting for each other.
So if we got rid of P3 to P4, P4 would no longer be in a deadlock.
If we got rid of what?
The P3 depending on P4, if we got rid of that arrow right there, P4 would no longer be involved in the deadlock. Is that correct?
Okay, so if we eliminate this,
Yes.
yeah, so in this case, P4 will not be involved
Okay.
in a deadlock. Okay, so the processes that are involved are the processes that are dependent or waiting for each other, and these are 2, 3, 4, 5. Now, to make the system deadlock free, so the answer is 2, 3, 4, 5, F. To make the system deadlock free, which processes should we terminate? So the rule is, to make it deadlock free, any process that is on all cycles can terminate the deadlock. So a process that is only on one cycle is not going to eliminate the deadlock. In particular, P4. So if I terminate P4, I will still have a cycle. But P2, P3, P5 are on both cycles. So if I terminate one of them, the deadlock will go away. So terminate any of the processes that are on both cycles in this case. 3, 4, 5. So the answer is 3, 4, 5. 3 or 4 or 5. Okay?
2, 3, 5.
Yeah, 2, 3, 5.
Oh, yeah. So, okay, so let me know. This is on both cycles, this is on both cycles, and this is on both cycles, and 4 is not on both cycles. So 2, 3, 5. And 2, 3, 5. Okay, last question. And last question, you'll have to draw it too. So consider a system with three processes and three resources. R1, there are two instances of R1, and R2 and R3, there is one instance of each. And P1, process P1 is currently holding an instance of R1. P1 is holding an instance of R1. And requesting an instance of R2. P2 is holding an instance of R3. P2 is holding an instance of R3. Holding an instance of R3 and requesting an instance of R1. And requesting an instance of R1. And P3 is holding an instance of each of R1 and R2. P3 has an instance of each of R1 and R2. And is requesting an instance of R3. So which processes are involved in a deadlock? Now first we try to resolve this. You try to find a process that is not, that can make progress and it's not holding and waiting. In fact, if you analyze this, I think it's a good idea to start the analysis by looking at the resources of single instance, because these will make things easy. P1 is waiting for an instance of R2. This means that P1 is necessarily waiting for P3 because of the single instance. So P1 is necessarily waiting for P3. And P3 is waiting for an instance of R3, so it's necessarily waiting for P2. So we know these dependencies or waiting relations for sure. Now what's the status of P2? P2 is waiting for an instance of R1, but there are two instances. One of them is with P1 and one of them is with P3. So P2 is waiting for either one of these two. So P2 is either waiting for P3 or waiting for P1. But in both cases, there will be a cycle.